Yeah, it's okay. Uh, Good morning, everyone. So I'm Omprakash Ramalingam Rethnam. I'm an assistant lecturer at Technological University Dublin. So the study that I'm going to present today is climate change induced overheating risk in Irish dwellings, assessed through machine learning technique. The co-authors are Ciara Ahern and Mark Mulville. Both are from the same university, Technological University Dublin. We are of a, we are the research group is called as Built Environment Research and Innovation Center. We are part of that, as well as Irish Building Stock Observatory. This project is a miniature snapshot of a bigger project, which is called as CCDOM, that is expanded as climate change related domestic retrofit overheating risk mitigation. What you're seeing on the right is the overall vision of CCDOM. What Ireland especially is in need of energy security, so we are marching forward to make homes very energy efficient, and because of that, there is a huge amount of large scale retrofit that is happening. However, with retrofit, there is an anticipated risk because of the climate change that also leads to dwelling overheating risk. So one of the some of the important deliverables that will be coming out of the project are tools and techniques that we will be giving to policymakers, that they will be able to test easily to understand what are the mitigation strategies that can be adopted now to mitigate overheating risk. And the end outcome is that we don't just move for energy efficient homes, but also focus on safety and health. So the motivation of the study, what we understand is not just the regions with warm climate, but even regions with cool climates are warming fast. The temperate dwellings, especially in Ireland, have been designed to retain heat in. We have designed it for a long heating season with no or very less active cooling systems involved, like air conditioners that are very airtight with no air permeability or with no air leak, and with highly insulated fabric. However, this becomes a liability during summer. We can see that around 50 to 85% of internal heat fatality rates are reported, and on top of that, they overlap with fuel poverty, where active cooling is almost unaffordable. And most overheating studies have been predominantly done on warmer regions, and overheating is now emerging in temperate and even in energy efficient in regions where energy efficient homes are the focus. So the research gap is built upon three pillars. The one is the geometric blind spot, which I already informed in the before slide, where you have limited research on overheating studies in cool climates. And then the second one is the overheating standard. We do have many standards, like SASBE is one of them. But one of the issues with SASBE is that the design summer year, or the weather file that it considers, is midterm and not long term. When during the course of the presentation, you will be able to see the implications of that, and hence the overheating compliance standards that are currently in place will not hold, or are not ready to for the coming summer because of climate change in the future. So every single building is designed for 50 years, like generally speaking. And when you design it for 50 years, then it is also expected that you consider the long-term future weather, so that your building is already resilient. So that these are some of the research gaps that are identified. And on top of that, the standards do have room level compliance checks, but they don't give you a simple metric to get a unified overheating assessment that can be done at stock level. So this study tries to do two things, to just summarize what is there in the slide. One, to quantify the migration of buildings that changes the risk bands when you go across the climate horizon. So in simple terms, you're trying to understand a building, you're trying to see whether a building is going to move into a higher risk zone, overheating risk zone, as the climate progresses. So that's the future weather. So the midterm, long term, and the present. So that's what we're going to quantify. And then the second one is to see what building envelope features play a significant role in this migration that is coming in, or that we are going to see in the dwellings. So the one is to quantify that is to measure the percentage of overheating risk migration when you go towards the future weather. Two, to understand what are the significant building envelope features that are responsible for this migration. So the methodology is put here. First, we start with climate data acquisition. We have Met Éireann's present and future design summer year files for Dublin. We create a simulation matrix, a full factorial simulation matrix with all set of envelope configurations that are in line with the building regulation standards of Ireland. And then you go with parametric dynamic simulation, where the simulation engine that is used here is IESBE, and across 3 climate horizons. The overheating risk assessment in this study is based on SIPC TM59, that is for domestic overheating compliance standard. And then we do the analysis for risk migration, and then trying to find out what drives this using ensemble machine learning based attribution. Just to talk about the climate file, what you see here is DS, DM, DL. D corresponds to Dublin, S is short term. So Dublin short term, Dublin midterm, and Dublin long term. So we are going to understand how buildings behave in all these 3 climate horizons. And just to, in the interest of some of you, what generally the standard tries to adopt DSY1. There are 3 set of climate files. That is, even in design summer, one is moderate event, most intense event is DSY2, and then prolonged event is DSY3. Generally, DSY is considered for the compliance, and we have also taken DSY1 and doing it for short term, midterm, and long term. And this is the parametric design space where you see orientation, thermal mass, air permeability, wall heat transfer coefficient, window heat transfer coefficient, and window G value. So solar heat coefficient value. So you have around 288 configurations per horizon, which totals up to like around 900 configurations when you count all 3 climate horizons together. What we are going to see is the left side is the tracking of the risk migration. We are going to see how buildings are going to change their risk bands as they move across different climate horizons. That is one. And then the random forest surrogate is going to help us to identify what drives it, as I said to you earlier. And this is just accurate, like to check whether our machine learning model is behaving accurately, and the fidelity checked based on the root mean square, the R square value and the mean absolute error. This is tested on test sets as well as the 5-fold cross validation. So this is the headline, I would say, slide for this study. What you see here is, if you see DS to DM, that's the let us talk about the figure 2. DS to DM is as the buildings move from short term to mid term, the green color indicates that the buildings are migrating from low risk to moderate risk, and the amber indicates the buildings are moving from moderate to high risk. So what you see here is, when we move from short term to mid term, the amount of migration is limited. And then once you shift the climate horizon, and once you come to from mid-term to long-term and short-term to long-term, what you see here is around 10.4% of the configurations within that typology changes its risk band. It moves from low risk to moderate risk, and 3.8% moves from moderate to high risk, and around less than 0.5% moves from high risk to very high risk. So what we are seeing here is 1 out of 10 buildings or 1 out of 10 configurations within that typology is changing. They are changing their risk bands when we are considering the long-term climate scenario. So hope that was clear. And the rise is incremental, not sudden, especially because when you're talking about short term to mid term, it's incremental. But when you're talking about long term, the warming clearly amplifies the risk, as we can see in the figure. And now we took the machine learning surrogate. The random forest is used here. What? How much time I have? 1 minute. So what you see here is. To just explain you in short, when we move from short term to mid term, what drives that migration of risk is the wall U value and the window U value. But when we talk about a long term, the highest, the most significant contributors are, or the most significant contributor is the solar gain. And then comes the thermal mass, and then comes the air permeability. So and those long term, when we're talking about migration at long term, they are changing bands from even mid risk to high risk. So they are the key components to consider in the analysis. So the implications: highly energy efficient buildings doesn't necessarily mean that they're safe. As we just saw, that a very airtight building can be can be a threat in when we take overheating into account. And then your building envelope should be carefully designed to cater to the future weather, and that should be included in the regulations. That's the motivation for the study. And the method made is general, so although it is applied to Irish case study, you can still implement it in your own region. The method is robust. And the key takeaway, I don't want to repeat myself, but it is just to tell you in short, the heating risk is gradual, the heating risk migration is gradual, but it is being amplified as weather worsens. A fraction, around 10% of the buildings configurations shift their risk bands as we move towards long term. The solar heat gain is the most important contributor that you have to focus for mitigating overheating. And then going with the right design, with the right mix of building envelope, that also considering the future weather, will make your building more resilient. Of some of the limitations of the study, we did not consider occupant behavior, urban heat island effect. Passive cooling strategies are not considered. Of course, we are now working to extend this beyond this typology, the apartment typology, and to extend to other climatic, to include other climatic regions. What we have done is that the surrogate is wrapped as an interactive web tool, and you can see that you can play with the building configurations based on the rich data set that we have generated from the parametric simulations. And you can scan the QR code to go and have a check on your own to play with the model. You will be able to see whether you're building the apartment typologies in high risk or low risk in the context of overheating. Thank you, and I'm happy to take any discussions. Thank you.
Thank you, Omprakash, for the great presentation.